Welcome to my classroom. I am Nesli. In this video, I shall try to explain how the difference between the extracellular and intracellular concentrations of calcium can produce an electrical potential difference between the two sides of the membrane, and this is going to be called the Nernst potential. For this purpose, I am going to design an experimental setup. First, there must be a concentration difference for calcium. We know that for every cell, intracellular calcium concentration is lower than the extracellular. Second, we must have channels for calcium. So I have placed these channels on the cell membrane. Third, the accompanying oppositely charged ions should not be able to pass through the membrane. What do I mean? For example, in the extracellular fluid, the accompanying ions are the negatively charged ions. They are bicarbonate chloride, so there must not be any channels here. So these ions, the anions, accompanying anions, cannot pass through the membrane. At the end of this experiment, we are going to obtain an electrical potential difference. Therefore, I do not want to have any electrical potential difference at the beginning. So whatever I find at the end of the experiment must be due to the concentration difference. That's why I placed electroneutrality on the intracellular and extracellular fluids. And more important than this, I have placed equal amounts of positive and negative charges on both sides of the membrane. So inner and outer sides of the membrane are also electrically neutral. Now that the experimental setup is ready, we can start. We have a force, concentration force, and channels. They can come together and calcium can move into the cell. At this point, I'm going to use arrows to show the forces. The length of the arrow will be the size of the force, and the tip of the arrow will show you the direction in which this force is pushing our ion. I also have a color coding. Black is showing the chemical force. Yellow will show the electrical force that this chemical force is going to produce, and the green is going to show the net electrochemical force, the sum of the black and yellows. So we have a high concentration outside. This is going to push through the calcium channels into the cell, and so my arrow is towards the interior of the cell. At the beginning, we do not want any electrical potential. Every part is electrically neutral, so we have a 0 for yellow. Then we can calculate the electrochemical force. What is it? The electrochemical force is equal in size to the chemical force, because chemical force is the only force here. So with this force, calcium is going to move through the calcium channels into the cell. So let's take it into the cell. The negatively charged ions, as we have told at the beginning, are not going to move because there are no ion channels for them. So now, with this effect, an electrical potential difference is produced between the two sides of the membrane. A small detail here. The positively charged ions do not move away from the membrane. Negatively charged ions do not move away from the membrane to the extracellular fluid because they are able to attract each other over the membrane, that they stick to both sides of the membrane, and this is producing a membrane potential. Now we have an electrical force that we can show by yellow. The positive end of this electrical force is inside the cell, and calcium is also positively charged. So positive charges repel each other. This means that the electrical force has to be outward. What about the chemical force? The chemical force is going to stay the same. For sodium, potassium, chloride and calcium, we need to know that the number of ions that move across the membrane is big enough to produce an electrical potential difference, but it's not big enough to change the concentration difference. There's a little bit of extra for calcium, which I'm going to explain at the end of this video. So, as calcium moves in, the chemical force will not change. If we calculate the net force, the electrochemical force is getting smaller, but it is still towards the interior. So we still have a force that can push calcium into the cell. More calcium goes into the cell. The accompanying anions cannot follow it, and the electrical potential difference between the two sides of the membrane is going to grow. It's going to get bigger. Practically, we said that the chemical force and the concentration gradient is not going to change. So as the electrical force grows, the net force is going to get smaller. But still there is a force, and more calcium ions will continue to move into the cell because the net force is still inward. Negative ions cannot follow, excuse me, and the electrical potential difference will grow bigger. As usual, chemical force is not going to change. There won't be an important change, but the net force is going to get smaller. Okay, how many steps do we need? When is this going to stop? What will happen in the end? Everything will come to an equilibrium point when the concentration force produces an electrical force equal in size to it and in the opposite direction. This electrical force produced here is called a Nernst potential or equilibrium potential. There is equilibrium because these two forces are equal and in opposite directions, and there is no net electrochemical force. This means there is no net calcium movement for calcium current. What is the use of this? This way we have an opportunity to express the concentration force in two units. One is millimolar, but if we use the Nernst potential, we can express it in millivolts, and this way we can use it to find the net electrochemical force. So here in this example, in this experimental setup, I tried to explain how the concentration difference for calcium can produce a Nernst potential on two sides of the membrane. How we use the Nernst potential is explained in another video. Before ending this, I need to give a little more detail about calcium. Calcium is a little bit different than sodium, potassium, and chloride. If you have a look at the concentration of calcium in the extracellular fluid, it's 10 to minus 3, and intracellular fluid concentration is 10 to minus 7 millimolar. If you say that there is 1 unit of calcium inside, there is 10,000 units outside, because the concentration is 10,000 times greater than inside. So if, let's say, we said that there's a small number of ions that's going to move inward to produce the Nernst potential. Let's say 1 moves inward, so this unit here is going to decrease to 9,999, and there will be 1 unit addition to the intracellular fluid. So let's have a look at the numbers now. The concentration outside did not change a lot. The concentration difference between inside and outside was 10,000 to 1. It became 9,999 to 2. This is not a very big change in concentration either. So I told you as I was working that the concentration force does not change a lot, but something changes. It is the intracellular concentration of calcium. Extracellular concentration does not have an important change. This high intracellular concentration gives calcium two two duties. One duty of it was to come in and produce an electrical potential. The second duty is chemical. For example, for the heart muscle to be able to contract, calcium from extracellular fluid must enter the heart muscle. This calcium is going to start the events that produce the contraction. The second example for a chemical effect of calcium inside the cell is at a synapse. At the chemical synapse between two neurons, the presynaptic neuron is going to release neurotransmitters to affect the postsynaptic neuron. And the release of neurotransmitter depends on entry of calcium into the axon terminal of the presynaptic cell. So here I tried to explain the Nernst potential for calcium and how it can be formed by an experimental setup. I hope it was useful. Thank you for listening.